Z target, then your reorientation effect should be enhanced. Suppose you take, like you took beryllium 10, where you could enhance the spin effect, because beryllium 10 has got spin 3 plus. So you could enhance that spin orbit effect.
Yeah,
so,
but for the boron 10, I also consider the reorientation, right? So it's, but the important channel when I find out is the spin orbit. So the spin orbit make it different, but also I also included some reorientation, because included the reorientation in the Fresco code is very easy. All you have to do is the two possible combination for the projection. So it's not so difficult, but suppose the effect is important.
We want to enhance the reorientation effect. Whether if we use in boron 10 on lead, higher Z target, whether this reorientation effect will be more?
Well, to be honest, I don't know. I have to check that. That's a good question. I don't know. I would expect yes, but I'm not so sure. We have to check that. As I didn't check. I didn't think about it, but I will check.
Yeah. This is very nice. Achha, one more question I just want to ask. This damping of nuclear Coulomb effect for this boromium nuclei. Why it gets damped? So any.
Let me show here. You see, that's usually the strong effect of the weakly bound nature of this nucleus is to get the dumping of this Fresnel peak. The Fresnel peak is an interference between Coulomb and nuclear potential. So if you have this near side and far side, and the near side, you have a smaller influence of the nuclear potential, and here we have a stronger influence of a nuclear potential. So it means if your system is weakly bound, it means your potential also might be not so hard disk structure. You have a more diffuse surface, and because of this diffuse surface, the effect of this interference is small, and this peak disappear or dumped. So this peak is more like it shows up when you have a hard disk approximation works fine. So for very tightly nuclei, this approximation of hard disk approximation works fine, and then we can have only the influence between the Coulomb and the nuclear potential. But in case of a weakly bound nature, this is a diffuse surface. And so this interference between the two, Coulomb and the potential, is more or less affected or smoothed, and you have strong absorption. And if you have a stronger absorption here, you dump this peak. So that's why usually this is one strong characteristic of angular distribution for weakly bound projectile. You have a dumped of this Fresnel peak.
Very nice. Okay,
Dr. Naik, there is one Ashok Mahajan. He's having a question.
Sure.
Dr. Mahajan, can you ask your question? Okay, meanwhile, I wanted to comment something and ask the question. If this thing weakly bound nucleus is deformed, highly deformed, like we had shown, would there not be any coupling between the angular distribution of the breakup fragments and the reorientation effect?
I think it's two different effects. So we did not consider the reorientation when we have this weakly bound, because the model we use to describe the breakup is this CDCC calculation, where we consider explicitly the interaction. I will show here. Explicit the interaction of it here. we have explicit the interaction between this cluster and this cluster. So we do not consider the projectile as a whole. So the deformation is not important. What is important is the description of a cluster configuration, which means this interaction and this interaction and this interaction. So when you do the CDCC calculation, the model we apply is what we call this cluster folding model. In this cluster folding model, we take explicitly this interaction. So we don't need to take this as a whole because we take it as individual cluster. So that's why here orientation is not considered.
But in principle, it can lead to, like, if the projectile is going to break up and it is reoriented, the angular distribution might become substantially different.
Yes, but then we have to take in a different way, you know, a different, we cannot take at the same calculation. So, or we consider the reorientation, or we consider in the CDCC. I don't have a plot where we did this individual approaches to compare these different approaches. So I don't have this information, but I agree. I mean, it's a different approach. Or we can do this reorientation, deformation, so on, or we do the cluster model.
Just one more query I had, that was regarding the 12 carbon, which can be considered as a cluster of 3 alphas.
A carbon 10?
3 alpha cluster, carbon 12.
A carbon 12, yeah.
A couple of years back, there was a PRL article which said that a linear chain of 3 alpha is also possible. So either they can be in a linear chain or on equilateral triangle. So has that been resolved experimentally?
Well, what I know is here. Yes, you see the carbon, you can have this 7.7 here, but you have this 3 chains or the 3 triangle, right? So that's exactly the point, how to investigate this cluster structure of this the carbon 12. And you have here all these models, and each of these models has some more or less different conclusions. I was reading this paper here, this first one, and it's indeed, it describes the data, describes the density as a triangle shape, this shape here. And that's a good discussion. That's what they are working on. I don't know if they have a defined conclusion, but I know they are working on these kind of things, and they have all this model. And I did not check if they are giving different results. And that's about something interesting to check. You know, how is the results in terms of carbon 12? I know they have already some comparison with the data. So there's some measurement, some density distribution measurement for this excited state in carbon 12. And they compare with the calculation, but I have to look for this paper. I don't have it here. I don't have it in my head, but I know they have done it. You know, there's some measurement. So this measurement can somehow test these models.
Dr. Mahajan, I think he's not asking. So, is there any other question?
Surjit has raised hand.
Who?
Surjit.
Okay, Surjit.
Surjit.
Hi, Valdir. This is Surjit.
Oh, hi. How are you doing?
Nice talking to you after so long time.
Yeah.
Actually, I missed your lecture as I had some meeting in the university. So my question is that have you can you comment about some reactions on astrophysical interest, if you have done any?
Yes, I have doing something, and I have some plans, some scheduled experiment. One particular experiment is going to be performed in January in Orsay with my PhD students. So the idea is to investigate the structure of magnesium 26. And the reason for that is because this magnesium 26 is very important for the neutron production in supernova and AGB stars. So they have this neon 22 alpha N reaction magnesium 25. So the compound nucleus is magnesium 26. And the interesting is for all these nuclei with mass close to the 30, between 20 and 30, the important states are above the neutron or alpha threshold. And the levels above this threshold is not well known. So the people doing several experiments to improve the level spectroscopy of these levels above this particle threshold. So I have been working this kind of experiment. So trying to improve the knowledge of the states, the spins, parity, energy, and if it's possible, the decay width of these levels for several of these nuclei close to the mass 20 and 30, some of them radioactive, some of them stable. Right now, I'm working, I was just seeing a talk here about carbon 12 plus carbon 12. I'm right now working in data analysis of magnesium 24. So I performed one experiment at Dorset, which is a PP prime inelastic scattering of magnesium 24, and I could excite the levels above the carbon plus carbon threshold. And I could see several levels which is not known. I don't know if I can get the spin particle for this level, but at least I can get the energy and I can confirm that there are several new resonance above the carbon plus carbon threshold. So that's what I've been doing. So actually, that's the two line of investigation I'm working on. So one is this elastic scattering and fusion induced by exotic nuclei, and the other one is this spectroscopy for astrophysics interest.
Thank you.
Okay. Well, nice to see you. Nice to talk to you again, and I hope I can visit India, in the near future.
I will be looking forward.
Yeah.
Myself and Basant and our Professor Godre will love to see you here.
I have with me here Professor K.C. Puria. He is head of the physics department, as well as one of the convener of this conference for physics track. Of course, I am thanking Dr. Baldir for accepting this invitation. You would like to say something?
Yeah, Honorable Professor Baldir, Professor Nayak sir, and Professor Surjit sir. It's a very pride for me. The reason is now very few university in India, they offers the theoretical physics as a specialization. So our university gives the specialization in theoretical physics. And as the theoretical physics is concerned, long before Professor Godre was saying that we are planning to organize a 1DA symposium at the Department of Physics, means my department. At that time, he was saying that I had contacted Professor Nayak and we will try to avail this opportunity. But due to this corona and other reasons, we are unable to organize such a great event at my university place. But at the same time, again, it is a pride for me that whatever the expectation we are keeping in our mind to organize such a great event, international event, Professor Godre has taken a lot more care to organize this theoretical session. Whatever the communication which is to be required to make with Professor Baldir, Professor B.K. Nayak, and Professor Mukherjee. So all this assignment is given to him, and he performed a very good job for me. At the same time, on behalf of my university, on behalf of my department, and on my personal behalf, I'm very much thankful to Professor Baldir sir for accepting our invitation and deliver a very beautiful and very informative talk, plenary talk. At the same time, Professor Nayak has chaired the session. So again, as the BRC is concerned, it is our neighboring institute, but as the interaction is concerned, I think we don't having the strong interactions. And Professor Gondre, okay, whatever the some weak interactions are there, this is because of Professor Gondre. So I'm thankful to Professor Nayak, Professor Mukherjee, as well as my dear colleague Professor Gondre. At the same time, as I mentioned that we are offering the theoretical physics, but now by the virtue of his age, Professor Godre is going to retire just after what you can say 2 days. On the 31st of October, he is going to retire. So it is a great loss for the department as a institution. At the same time, it is a unrepairable loss for me. As the basic what you can say studies, just like a classical mechanics and nuclear physics, I think he having a very good hold on the subject. So nowadays it is possible to avail a fresh candidate or a fresh lecturer, but it is very difficult to have a very intelligent and a good faculty in the department. So I think it is impossible to replace or to fill up the positions at the place of Professor Godre. He is a very senior teacher. He is a very you can say intelligent as the assignments are concerned. Whenever I am in the some guidance is to be required, he always work as a friend, philosopher, and the guide for me. So I feel proud that at the time of his retirement, just before the 2 days of his retirement, he can say take this assignment and he fulfilled the what can say our expectation. Students and all the faculty members are very much happy to what can say attend this lecture as well as this session. So once again, I'm thankful to Professor Waldi, Professor Nayak, Professor Mukherjee, as well as my dear colleague Professor Godre. So on behalf of my department, it is a proud privilege. It is a proud moment to felicitate my dear colleague in the presence of the giants of the field, giants of the field of theoretical physics. In the presence of Waldi, Professor Nayak, and Professor Mukherjee, it is my proud privilege to what can say felicitate my dear colleague Professor Godre.
Thank you. You both cannot fit into same frame.
Yeah.
We both are heavyweight, can't fit in same frame.
Okay, thank you, sir. Yeah, please, Professor Godre.
So once again, I thank Professor Waldi and Dr. B.K. Nayak for chairing the session. And very beautiful.
But you were so young to get retired. You look so young.
This is die, here die. I always believe age is what you think you are. If you stop thinking, then you
are old.
You are old. One must always feel young, always must be inquisitive. I was taking notes when you were saying, although I am retiring in 2 days, but I am not going to leave physics. I will always keep on learning and keep track. Thank you very much, sir. And Dr. B.K. Nayak, thank you very much for chairing this very, very long session.
It was my pleasure.
So now I invite. Yeah, you want to say something?
Professor Waldi, namaste.
Adio, Waldi.
Waldi.
Sorry.
Namaste.
Namaste.
Namaste from my side.
It was great to see you.
Nice to see you after so long time.
Yeah, okay. Well, as I said, I hope to see you all again in the near future. So let's just wait, to how this pandemic gets go away, and then we can meet again in some conference or even in India.
Maybe
so
next
thank you very much.
Maybe next year winter we can see.
Yes. Nayak, as I was mentioned, I was planning to organize a workshop here in São Paulo. I'm still planning to do it, but I'm going to postpone it to late next year, just because, you know, to wait things to get down in terms of COVID.
Okay.
But I will contact you.
Thanks for the information.
Okay, thank you.
Andre,
Yes,
wish you all the best for your new innings.
thank you very much.
We're going to start a new innings. As I know you, you are always you know, person who takes difficult problems, and you know, though you have very limited facilities, but still you work on that environment. I must salute you for your effort and your enthusiasm, and
Thank you.
I'm sure that you will keep continuing to do whatever you have been doing and whatever you feel like doing. Now there is no restriction of you know, going to department in a, you know, 9 to 5 or something. So now you have free mind, and you can really you know, do some wonder. What you have been thinking for so many years, you can do all these things. So I wish you with your family good health, happiness, and prosperity for time to come. Thank you.
Thank you very much. So I think I have to thank you very much.
Okay, thank you.
We'll now, I will ask Dr. Basanta Naik to continue, because
Okay.
his wife is not pestering him in the poster session as well. And Dr. Valdir, if you can. You come and take it up. I'll just tell you. So now I invite Dr. Surjit Mukherjee to chair the next session, which is the poster session, where 3 posters are there related to the same topic that we have been continuing. In fact, one of the paper is on the weakly bound nucleus. A new idea has been put up there by one of my students. And then 3 posters will be on material science subject. Dr. Surjit Mukherjee is a very good friend of mine, almost same age. He's going to retire next semester. Next semester end. Yeah. But age-wise, we are almost same, and you can see his hair also black.
A little less than yours.
And we have almost the same track. I did my PhD from IIT Kanpur, and I know that Professor Mukherjee did a project there in IIT Kanpur, but unfortunately it was just after I left. Then Professor Mukherjee was there. He did a postdoc in many places, and then finally he was in Vikram University as a lecturer, I suppose.
Yeah.
And then he has ended up in Baroda, very near to me once again, in MS University. And he is doing great job in nuclear experimentations. Many students have done PhD under him. I'm happy that one of his students is very nearby, is only about 10 kilometers from here, whose first talk was there in the oral session. I do intend to meet him in his institute sometimes, never finding time.
In fact, 2 students are near to you.
Who? Who's the second one?
One is Deepika Patel, who is in NIT.
I forgot. Anyway, that's another story. I have to blame BK Naik for that.
Yeah.
Anyway, she would have done PhD under me, but she's also very good student.
She's a very good student.
Hard-working student. Yeah. She's in SVNIT now.
Yes.
So since we already spent a lot of time and it is nearing about the time to end, but we are going to begin. And I will ask Dr. Surjit Mukherjee to now chair the session. Since there are 6 posters, maybe we can allow 5 minutes or so for each poster and then some question session. Yes. My colleague, Dr. Jitendra Dhimar will take over, because he has the technical knowledge about how the posters are going to be presented in this online platform. So, Dhimar, please come.
Thank you. Thank you, Professor Godre. And I thank you all.
I'm here.
Yeah. and I thank you all for giving me this opportunity to chair the session. So without wasting any further time, may I start? Can we start now?
Yeah.
Okay, so we can start with the first poster. Semi-platonic, semi-leptonic decay of lambda B baryon, Kaushal Thakur.
Sir, just give us 2 more minutes.
Hello everyone. Myself, Dr. Coulomb, Assistant Professor in Government College, Daman. I welcome you all in my today's presentation on study of the semi-electronic decay of the lambda B baryon. It is a great privilege for me that I got chance to represent my work on this platform. Here we see various decay channels available for lambda B baryon.
I think he has lost connection.
Hello.
Hello. Yeah.
Sir,
Yes.
always-
Yes, you can continue.
Okay.
Yeah. Okay.
All these experimental measurements and theoretical calculations make the study of semi-electronic decay of lambda B baryon very interesting. As we know that the exact solution of the QCD equation is very complex. So one has to rely upon a conventional quark model. Here to study the semi-electronic decay of lambda B baryon, I have adopted hypercentral constituent quark model. The hypercentral approach has been applied to solve bound state and scattering problems in many different fields. The two relative coordinates, rho and lambda, that is indicated by this, are rewritten into a single 6-dimensional vector which is known as the hyperradius X. Here, the quark wave function for the HCQM can be factorized in 2 parts. The first part of the wave function, which depends on the hyperradius, will give you information about dynamics of quarks, while the second part will give you a geometry of the quarks. The second part of the quark wave function is the hyperspherical harmonics, which satisfying the eigenvalue relation given by the equation. When we use hyperspherical coordinates, particularly in the center of mass frame, when R center of mass is equal to 0, the kinetic energy of operator that can be written like this equation. And if we choose the interaction potential is hyperspherical such that the potential depends only on the hyperradius X, and the hyperradial Schrödinger equation can be written by this equation. So the 6-dimensional radial Schrödinger equation described by this equation is solved in the variational approach with the Coulomb trial radial wave function, which is given by this equation. The confining 3-body potential is chosen within a string-like pictures where the quarks are connected by gluonic string and the potential increase linearly with the collective radius X. When we choose approximation, which is known as the heavy quark mass, particularly in this approximation, the 6 form factors defining the semi-electronic decay of lambda with baryon are related only with the Isgur-wise function. In the literature, various approaches exist to calculate the Isgur-wise function in absence of any standard formula. Here, the Isgur-wise function can be calculated using Taylor series expansion at the zero equal point. So, finally, we can calculate the Isgur-wise function from this equation in hypercentral constituent quark model. Here, omega, which is related to the square for momentum transfer between the heavy baryon Q square by this equation. The Isgur-wise function for the weak decay of heavy baryon can be written by this equation in HCQM. Here, the psi square comes into the picture instead of overlap integral of the final and initial state. This is because we have investigated the Isgur-wise function at the zero equal point. It means when omega equal to 1, we are calculating this, where the four velocities of baryon before and after transitions are identical. So after substituting the expansion of this cos px into this equation, one can able to derive slope and the curvature of the Isgur-wise function in HCQM. Once the Isgur-wise function is obtained, one can be able to predict the semi-electronic transition of heavy baryons via the differential decay. Here, iota is the ratio of mass of the lambda b to the lambda c baryon. The slope at zero equal point
You have completed 5 minutes.
of the baryonic Isgur-wise function is computed, and the result along with the other theoretical predictions are listed here.
Hello, Mr. Thakur. You have completed 5 minutes.
Give you the information about
Professor Surjit, this is a
Yes.
recording. This is recording, and it is for 6 minutes. It will be over in its time.
Achha. Okay.
decay width of semi-electronic decay, while this third column indicates the branching ratio of particular lambda b to lambda c baryon. Finally, we can conclude from the result the calculated or the computed slope in Isgur-wise function is fairly agrees with the other theoretical predictions. And when we talk about decay width of this lambda b baryon, the calculated result will very much comprehensive, or you can say it is in good agreement with the experimental value. So here we can say that the hypercentral constituent quark model gives plausible predictions for the Isgur-wise function for this study.
Yeah.
Next one question.
Dr. Surjit,
Any?
that recording thing is over. If
Okay.
anyone wants to ask the question,
So,
or you have a question.
Now I invite any questions are there, so you can ask.
Yeah. I have two questions. Can you tell me why you are telling it semi-leptonic means what?
Mr. Kaushal Thakkar, are you here?
Hello.
Mr. Kaushal Thakkar. I
Hello,
think
I think he has lost.
he has lost.
Okay,
He has
so let
lost.
us go
Okay,
to the next one.
next one.
Next one, let us go to the next poster.
Jigisa Patel.
Jigisa Patel and Professor Subodh Bodre, fusion cross-section for magnesium lead reaction.
And dear friends, my
And
name
please-
is Jigisa Patel and I am pursuing PhD under the guidance of Dr. Subodh S. Bodre sir. Today I am going to deliver my presentation on fusion cross-section for 24 magnesium plus 208 lead reaction in 3-stage classical molecular dynamics models. Let's start with the introduction. Fusion cross-section for heavy ion reactions have been calculated in various classical and semi-classical models. Fusion cross-section have been calculated for many reactions in 3CFD model using NN potential with a parameter set P4. However, the calculated physical cross-section do not match with the experimental data for many reactions at different energies. In the present work, we calculated physical cross-section for 24 magnesium plus 208 lead using potential of a reference 3, which is called new potential NP. Using this potential, physical cross-section have been calculated for 16 oxygen plus 92 zirconium reactions in a reference 3, which shows good agreement with the experimental data. So, the use of this potential parameter set might give better agreement in 3S CMD model for 24 magnesium plus 208 lead reaction. In a present work, physical cross-section are calculated using classical approximation and compared with the experiments. Now let's discuss calculation details. So here, first we generate the nucleus using the static code in which nucleon distribution is obtained by cyclically minimization of the initially random nucleus configuration of a given nucleus with a software Gaussian form of NN potential, which is given by equation 1. Now here table 1 shows before and new potential parameters set for the NN potential of equation 1, and table 2 shows the ground state properties of 24 magnesium plus 208 lead nuclei used in the present calculation. The dynamical collision simulation is carried out in a 3S CMD model, and this model proceeds in 3 stages. The first stage is Rutherford trajectory calculation, in which the two nuclei assumed to be charge point particles are brought along their Rutherford trajectories with given energies up to 2100 Fermi. The second stage is Crbd calculation. Crbd stands for Classical Rigid Body Dynamics, in which two nuclei are assumed to be rigid bodies and are allowed to evolve further using Crbd model calculation, which is continued up to a relatively small separation of 50 Fermi. And the third stage is CMD calculation, in which the rigid body constraints are relaxed at about 50 Fermi, and trajectories of all the nucleus are computed using the coupled Newton equation of motion for all the particles in a CMD approach. In the classical approximation, physical cross-section is calculated from the classical formula, which is given by equation 2, and that is sigma fusion is equal to pi VCR square, where VCR is the maximum impact parameter for which the two nuclei are fused. Now let's discuss result and discussion. Here, figure 1 shows the fusion cross-section for 24 magnesium plus 208 lead in a logarithmic scale, and figure 2 shows the fusion cross-section for 24 magnesium plus 208 lead in a linear scale. Here, that blue line shows the fusion cross-section. Sorry. Here, the blue line shows the fusion cross-section calculated using P4 potential parameter set, and that red line shows the fusion cross-section calculated using NP potential parameter set, and that blue dots are experimental data of reference 7. Now from the figure, it is clear that the fusion cross-section calculated using P4 potential parameter set are highly overestimated compared to the all experimental data at all energies. The reason behind for this overestimation is the larger root mean square radius of the 208 lead produced in this calculation as compared to the experimental data, which is shown in a table 2. The fusion cross-section calculated using NP potential gives close agreement with the experimental data. Now the conclusion. Although the fusion cross-section calculated using potential parameter set NP, which gives good agreement for 16 oxygen plus 92 zirconium reaction in a reference 3, however, it is overestimated for the medium heavy mass and heavy mass nucleus, that is 24 magnesium plus 208 lead. However, it may be noted that the ground state properties of the nuclei generated using this potential are not close to the experimental value, which is seen in table 2. Here, all are the references which I used in the present work. Thank you.
Okay, done.
Is there anybody?
Any question? Any question, please?
Yes, yes. I have a question.
Jignasa, are you there?
Yes, sir.
Okay.
Yeah. Here my
Go ahead.
question also, I will have some suggestion. So you have taken nucleon potential.
Yes, sir.
So then there will be so many nucleons, 24 in magnesium and 208 in lead.
Yes, sir.
So how do you do that calculation? That combination will be huge, no?
Sir.
Or you density distribution, or you integrate out, then you get a nucleus potential.
Sir, we use that static for to generate a nucleus,
Hmm.
in which nucleon distribution is obtained by cyclically minimization of the initially random nucleon configuration of a given nucleus.
Okay. Then ultimately you get a nucleus interaction.
Yes, sir.
So that then you get some distance of closest approach or something. So that B you are getting, B critical. Is it that how you get that B value? Ultimately your cross section is pi B square, no?
Pi BCR square. Yes, sir.
How you get that B? Are you hearing me?
Yes, sir. Yes, sir.
Or I will ask you some other question. Okay, you look into it. Just I want to understand it. And another thing is that how your this result will compare with the time dependent Hyperspherical calculation. Okay, you remember this what I told. And then what you do, there is going to be a school in IUSC, and I think registration is now open up to November 5th. You register there as an online participant, and there will be some few lectures on this time dependent Hyperspherical and things like that. So you attend those school. That will give a good idea about how these calculations are done.
Okay, sir.
You go to IUSC site, you see there is a school on reaction. So you just online register, and whenever that school will be there, you attend. There are some foreign speaker. They will be speaking on this Hyperspherical calculation, because your calculation is something like that. No, they are doing quantum mechanical Hyperspherical, so you are classical. So you will get a better understanding when you attend that.
Okay, sir.
Okay, all the best.
Thank you, sir.
Any other question? Jignasa, what do you mean by estimated data? That in your figure you have said estimated data. What is the meaning of that? Can you hear me?
Yes, sir.
Anyway, you think about it, discuss it.
Yes, sir.
Do you mean estimated data means calculated values, or what? What are you saying?
Or is it experimental data? What
So
is the
calculated.
Okay.
Okay, fine. Okay, then if there is no question, then we can move on to the next poster by Mr. Vipul Kataria. Event probabilities for 11 both beryllium 209 bismuth reaction multibody 335 CMD model calculation.
Directive time. Directive time. Directive time. Hello, Vipul Kadar, are you here?
Yes, sir. Yes. Yeah.
Wonderful. So
Online.
Uh,
Hello, Vipul. Hello, are you?
Yes, sir. I'm
Am I
able to hear you.
audible?
Yes,
Yeah.
sir.
Yeah. So you can explain your PPT or your poster. Okay. You are online, no?
Yes, sir. Yes, sir.
Yeah. You explain it.
Okay, sir. I'm presenting the video from my computer, if possible.
Yeah.
Okay, no
Whatever it's
Okay.
because because your voice will not come, voice are not coming out.
Okay, sir.
Very good.
Meanwhile, we can move to the next one.
Yeah.
Dr. Surjit,
Yeah.
while he is figuring out this problem with the audio, let us go move to the next one.
Okay, fine. So now I invite Mr. Ashwin Prajapati, study of axis Crbd correlation factor and axis Helmholtz energy for binary mixtures. Or maybe next one, Krishna.
Microordinate summation in the
Krishna micro.
Material science.
Material science.
Krishna Lekhin wala.
Sorry,
Yes.
sorry, Surjit sir. Yeah. Okay, now it's start. Krishna Lekhinwala.
Krishna Lekhinwala, okay.
Hello everyone, my name is Krishna Lekhinwala and title of my poster is Growth and Study of Bismuth Sulfide by Using Gel Method. Bismuth sulfide is belong to the family of solid state material which is useful in a photodiode arrays and in a cooling technologies. Now we have grown the bulk single crystal of bismuth sulfide by using a very simple and inexpensive gel technique. The standard condition to obtain such crystals were optimized and discussed, and the grown crystals are characterized by X-ray diffraction and scanning electron microscope. Gel technique. Crystals of bismuth sulfide were grown by a
Poster is
simple
not
gel
seen.
technique using a single diffusion method, and the
Poster
optimum
is
configuration was
not
established
visible.
by various parameters such as a pH of gel solution, gel.
So just a minute.
Poster is not visible.
Concentration, gel setting time, etc. And the crystals were grown by using a.
So is it now visible?
Yes.
Hello everyone, my name is Krishna Lekhinwala and title of my poster is Growth and Study of Bismuth Sulfide by Using Gel Method. Bismuth sulfide is belong to the family of solid state material which is useful in a photodiode arrays and in a cooling technologies. Now we have grown the bulk single crystal of bismuth sulfide by using a very simple and inexpensive gel technique. The standard condition to obtain such crystals were optimized and discussed, and the grown crystals are characterized by X-ray diffraction and scanning electron microscope. Gel technique. Crystals of bismuth sulfide were grown by a simple gel technique using a single diffusion method, and the optimum growth conditions were established by varying a various parameters such as a pH of gel solution, gel concentration, gel setting time, etc. And the crystals were grown by using a chemical reaction which is 2BiCl3 plus 3H2S equal to Bi2S3 plus 6HCl. Procedure. So we have taken a 5 cc 1 normal acetic acid into a small beaker into which sodium metasilicate of density 1.04 gram per centimeter cube was added drop by drop with a constant stirring by using a magnetic stirrer until the pH of the solution reaches to the 4.40. After that, H2S gas solution was passed through the gel solution for different time intervals like 5 minutes, 10 minutes, 15 minutes, etc. Then after 1 to 36 hours, when gel was set, the outer region BiCl3 was poured over the set gel and the crystal in small size were obtained and in yellowish white color after 30 to 31 days. Now this table indicates the optimum growth condition for gel method and the results was shown here. Now we have characterized our grown crystals by using X-ray diffraction and scanning electron microscope. So X-ray diffraction of gel grown crystals were recorded with the help of milliflex and in the range of 0 to 80 degrees. This is an X-ray diffraction graph intensity versus 2 theta graph. The observed values are very well matched with the JCPDS chart and observed peak in diffractogram indicates that bismuth sulfide crystals were orthorhombic in structure. And using the D value corresponding to the different phase, cell dimensions were calculated and the values of cell dimensions are A that is 11.6 angstrom, B that is 11.33 angstrom and C that is 3.91 angstrom. Now this table indicates the calculated and observed values of E and HKL. So the variation in cell parameters shows that the grown crystals of bismuth sulfide are not exact single crystals, but they are having a crystalline behavior. Another characterization method which we have obtained, that is scanning electron microscope. So we have taken a successive photographs at different magnifications. And these are the images of the gel-grown crystals. And that image shows that the heterogeneous nucleation process takes place. And in higher magnification, like 10K, which is this image, the shape of the particles like rectangular plate with no attachment of microcrystals, which confirms the control growth conditions. Results: we had grown bismuth sulfide crystal using gel technique and using a single diffusion method. To establish growth condition, we have changed the various parameters. In XRD, the position of all the peaks are in good condition with the JCPDS chart, and indexing of some major peaks in XRD pattern is according to the JCPDS file, which is basically used to calculate cell dimensions. And variation in cell parameters shows that the grown crystals of bismuth sulfide are not exact single crystals, but they are having a crystalline behavior. And in SAM, particles size varies and shape of crystal in gel growth method are large and rectangular plate. And references are mentioned here. Thank you.
Any question?
Yes, sir.
Vasant, you unmute yourself.
Yeah, sorry. I have a question. So, this you say
Mr.
that
Unmute yourself.
it has got application in photodiode.
Yes, sir.
So have you done any study in that direction?
No, not yet, sir. I'm just working on it. So far, I have done the characterization part, but I will work on it, sir.
Okay, characterization. What do you conclude that your structures are as expected?
Sorry, sir.
The structure of the material is as expected.
There are some variation, but yeah, the crystalline structure is there, sir.
Okay.
There is if there is no further question, let us move to the next. Who is going to speak?
Professor Surjit, Ashwin Prajapati. Ashwin Prajapati.
Yeah, then I invite Ashwin Prajapati.
I'm Ashwin Prajapati, and I'm going to present my poster presentation on study of excess transfer correlation factor and excess almost energy for the binary mixes. I belong to Department of Applied Physics, the Maharaja Saidinal University of Baroda. The present work is part of our own study on concentration dependent dielectric analysis of some neural alcohols with acetophenone. In the present study, we measure the static dielectric constant, which is 0, and optical dielectric constant, that is we can take an square of the refractive index of binary mixtures. Compare the binary mixtures of very concentration from 0 to 1, and to understand the molecular mechanism, we use the two approaches. One is the approach, and another one is the Reis and Diaz approach. Using both these approaches, we define the molecular interaction between the participating liquids. The major values of the static dielectric constant are in good agreement with the reported diffusion values. Reported values of the static dielectric constant and the refractive index are shown in table 1. Table 1 and these values are in good agreement with the diffusion value. Now, in table 2, we detect the mixing field parameters and the almost energy for the binary mixtures. The mixing field parameters of acetophenone mixtures, mixing field parameters of ethanol mixtures, and almost energy. We also plot the static dielectric constant values and the refractive index value. The values of the binary mixtures are noted in figure 1. Figure 1 shows the nonlinear behavior, and the nonlinear behavior, static dielectric constant, and the refractive index values indicate that the possible molecular interaction or micromolecular interaction between the participating points. In figure 2 shows the values of excess Crbd parameters. Two excess Crbd parameters are evaluated, like one is E1E, that is the excess of the parameters of the Coulomb, excess of the parameter methanol, that is ETE, and the E12 is the excess of the parameter of the the relation of all the parameters are the E1E the values of the excess parameters, excess of the parameter values of E1E is slightly higher than G1E and G1E. That as the conservation of the methanol, previous in excess, the G1E values fall rapidly. This indicates that as the conservation of the methanol molecules increases in the mixtures, this increase in the methanol molecules in the mixtures step to hydrogen bond in the mixtures. So the key shows the variation of the excess energy, excess dipolar energy due to the long range interaction between the particles. This shows the positive deviation. The figure 4 shows the excess dipolar energy due to the short range interaction, and there are two types of short range interactions. One is short range interaction between the light molecules and short range interaction between the unlike molecules. If you see in the figure 4, the magnitude of the short range interaction between the light molecules is very high, and it shows the positive deviation. It also follows the trend of the long range interaction. As you can see in figure 3, both follows the same trend. This shows that the formation of the beta type of modules in the binary mixtures. Last, here are some of the references which listed. This last, I also thank the organizing committee of Emerging Science in Life Sciences for giving me chance to present part of my work. This international conference on life sciences. Thank you.
Any questions?
Yeah.
Okay, let me ask a question. Wow, that sound was not very good.
Yeah, I agree.
Just tell our question that where we are going to use this dielectrics.
Ashwin, are you online?
Mr. Ashwin?
Professor Surjit, he is not
Yeah.
online.
Okay.
Okay,
So we will go to the next Deepali Chokawala.
Okay. So Deepali Chokawala.
Yeah.
Micro hardness studies.
Good afternoon, everyone. My name is Dr. Deepali Chokawala. I am from South Gujarat. Today, my topic is micro hardness studies on macrowire of bismuth samples. Bismuth is a bulk form in semi-metal and therefore is not a good thermal electrical material. The nanowire of bismuth have a thermal electrical figure. While using the semiconductor behavior, empirical characterization is an important formation of nanowire of different materials. In present communication, the micro-hardness testing of bismuth wire phase samples was carried out on microscopic scale. The variation of Michel's number are reported. Indentation size effect was observed for the bismuth wire phase samples at a low intensity. The variation of micro-hardness number with the variable load is not systematic for all the samples. The classical Meyer flow and proportional statement resistance model were used to analyze the micro-hardness behavior. Using crystal empirical relation, elastic stiffness, constant threshold characteristics from the hardness data. Metal of iron pure was obtained from the nuclear fuel complex Hyderabad. Macrowire of the bismuth material was prepared by melting the bismuth metal in a detail, and end of the detail was connected to 1 meter long and 1 millimeter diameter wire on the material. The current supplied to obtain the melting temperature of the bismuth material. The molten cells are moved in a capillary, and after cool, slowly a very fine, nearly 20 centimeter long wire was found, as shown in the figure. The wire was sliced by the thin plate and indented on the vesicle microhardness. Unions were made using the pyramidal diamond center. The measurements were carried out on the for the sample for a load ranging from 10 grams to 120 grams for the sample. The test certificate was the time of the test certificate was that constant. A number of the unions were made at each load and at the random on the structure. The mean diagonal length was 2 unit activation. Because microhardness number is obtained for each sample. To obtain the general behavior of the average of 20 samples at each load were drawn. Because microhardness profile as a function of the applied test load for the bismuth wire is sample. As shown in the figure, it is evident for the figure 1 that the microhardness of these samples decreases with the increase in applied load. At a higher load, it becomes constant. The decrease of the microhardness is increased with the load is a good agreement with the normal indentation size to factor ISQ. Further observed by the value for 30. Order to describe ISQ layer of the material, several models for the relationship between applied indentation source and indentation diagonal length have been reported in the literature. Most common estimation of the ISQ found in literature is directly related to the intrinsic structure factors of the test material. According to the theory, in order to analyze ISQ, hardness testing one needs to fit the experimental data according to the mineral flow, which correlated with the applied test load and resulting indentation size difference in each other. For the present research work, the expression shows that the hardness decreases with the increasing load. That is, n is less than 2. N is the work hardening coefficient, and according to the condition, n should be lies between 1 to 1.6 for the hard material and above 1.6 for the softer one. The value of n for all the samples above 1.6. So it suggests that our samples belong to the soft material category. Recently, UNZ extended the ISQ with the help of the general model proportional displacement resistance. As can be seen in figure 1, actually for all bismuth samples attain the saturation value at a higher load can be extended by the PSR model. According to PSR model, there are two factors which are responsible for the decrease of the hardness with the increasing load. The first one is the frictional force between the test specimen and the test, and the second is the elastic resistance of the test material. In PSR model, P and N microhardness can be described by two different parts. First part is the indentation load dependent part, IS or IS region, and second part is the indentation test load independent part. The first order elastic stiffness constants, a given one of the sample are calculated using Buster's empirical relationship as shown in the table. Work hardening coefficient found to be greater than 1.6 for bismuth wire sample. So we calculate that the bismuth is soft material extremely ductile, and also suggests that there is a possibility in decrease of the wire diameter. Thank you.
So I'm sorry, I could not, it was not visible properly, the poster.
Yeah.
So we cannot say anything. If anybody has any question, we can.
Yeah, I can just ask. I was just wondering, what do you mean by micro hardness? How to define? I was looking but not able to see, as Professor Surjit told. How do you define this micro hardness?
Deepali, are you online?
I think she is not there.
Yeah, she is not there. Okay, so we have to go to the next one.
Can you come and can you unmute yourself and answer?
Doing high pressure. Good.
Chokawala?
Professor Godre,
yeah,
she is not online.
She is not online. So
Fine.
we go to the last poster, I think.
Last.
Vipul Kataria.
You solve your problem?
People, are you ready? Vipul, are you here?
उनको पहले बोल दीजिए टॉप का बाद थोड़ा रोकेंगे, भाग नहीं जाएंगे जैसे टॉप खत्म होगा तो उसके बाद रोकेंगे.
all of you should not leave. Remain here for some time more.
Question answer session.
Yes, sir, I'm sharing my video screen with you.
Okay. Still your voice is not clear. Vipul Kataria?
Yes, sir.
Still your voice is not clear. Please explain your.
What, sir?
Your voice are not coming out.
Okay, sir. Let me just present this slide and there is a oral.
Yeah. Now we have got it. Okay. Okay. You shall start.
Okay, sir.
Okay, fine. Speak.
Okay, sir. So what we have done here is we have tried to calculate the event probabilities for 11 beryllium plus 209 bismuth reaction in multi-body 3 HCMD calculation. So for this calculation, first of all, the projectile 11 beryllium is having a 1 neutron halo structure, and it is having a very weakly bound neutron with the neutron separation energy is equal to Sn is equal to 0.501 MeV. So the breakup of such weakly bound neutron can be prominent in the nuclear fusion reaction. So to study the such breakup effect, this effect can be better investigated with the heavier target, for example, like 209 bismuth, due to its long range predominance of Coulomb reorientation. So here we have carried out the simulation of 11 beryllium plus 209 bismuth using the multi-body 3-stage classical molecular dynamic model, in which this 11 beryllium is constructed as a cluster of tightly bound 10 beryllium plus 1 neutron. Here for the construction of 11 beryllium, we have during the simulation, we have treated the 10 beryllium of 11 beryllium as a rigid during the calculation, and the bond between 10 beryllium and neutron non-rigid during the calculation. Okay, and for present calculation, we have calculated event fractions and event probability from this reaction. Now, here are the calculation details. For the construction of target and projectile, we have used the phenonomic soft core Gaussian potential, which is given by the equation number 1, and the potential parameter set for use for this potential is V0 is equal to 710 MeV, C is equal to 1.88 Fermi, and R0 is equal to 1.15 Fermi. And the ground state properties of the generated nuclei are tabulated in table number 1. Here, we can see that for the construction of beryllium 11, we have used a dynamic cooling method, which is mentioned in the reference 2. In this method, we have tried to find out the equilibrium orientation and position of center of mass of the constituents of 11 beryllium, which are 10 beryllium and neutron, and such equilibrium orientation and center of mass position have been obtained. Now, the center of mass separation between 10 beryllium and neutron is adjusted in such a way that the typical ion potential between them is equal to the experimental neutron separation energy of 11 beryllium. Now constructing this projectile, we have tried to calculate the event fraction FB, which is given by the equation number 2. Here in the equation number 2, and events indicates the total number of events. For example, complete fusion, direct reaction like a neutron transfer or scattering, and total are the total randomly initialized trajectories for the given reaction. We have also calculated the event probabilities, which is given by equation number 3, in which we have integrated the equation number 2 from B is equal to 0 to B is equal to B maximum, where B maximum is the impact parameter above which all the trajectories results into the scattering. Now, resultant discussion for we have calculated event fractions for 3 different energy out of these 3 energies. 2 energies are the near barrier energy, and one energy is the far above barrier energy. For the near barrier energy, for example, E center of mass is equal to 38 MeV and E center of mass is equal to 40 MeV. It can be seen that for the lower impact parameter, the green line which indicates the neutron transfer from the projectile to target, it's significant. And for the higher impact parameter, almost all trajectories results into the non-breakup scattering. Now, for the far above barrier energies, it can be seen that for the lower impact parameter values, most trajectories result into the direct complete fusion, while for a slightly higher impact parameter, we can see that there is increase of neutron transfer or neutron transfer reaction from the projectile to target. And for the higher impact parameter, most trajectories will results into the scattering event. Now we can also represent this in terms of event probabilities for different energies. Here we have event probabilities such three events like direct complete fusion, which is represented by this purple color, the incomplete fusion of neutron, which means that neutron transfer reaction, which is indicated by this green color, and non-breakup scattering, which is represented by orange color. So here we can see that as we increase the incident energy, the scattering probability decreases as well as the direct complete fusion increases. But we can see how the neutron transfer is dependent on how the projectile or what impact parameter the projectile is approaching the target. And these are the list of references which we have used for the presentation or for this poster. Thank you.
Any question from the audience?
Yeah, I have a question.
Yes.
Yes, sir.
I find this calculation is very interesting. दिखा ना थोड़ा figure दिखा.
Please share your screen again.
Vipul. Vipul. Am I audible, Vipul? Are you online?
Yes, sir.
Yeah. So share your screen.
Yes, sir.
Yes. So this figure you are showing, one is transfer, which is green, and
Yes,
one
sir.
elastic, one is fusion.
So these are just the estimate of what are the chances of different events during the.
What is this red curve?
So that red indicates the scattering events, non-breakup scattering, which projectile is not breaking up.
Projectile is breaking up or not breaking up? Not breaking up. Can you just explain this one? These three. Your low energy. What is red? I understand your green is you are telling neutron transfer.
Yes, sir.
That looks good because as the energy increases, it became bell shape.
Yes, can you make that diagram a little bit bigger?
So बड़ा कर दीजिए.
Yes, sir. So is it visible?
Yeah.
Yeah. Okay.
Red is your incomplete fusion.
So red is the scattering events. Green one is the neutron transfer reaction.
Inside what? You have a beryllium 11. What you are detecting?
Sir, we are just calculating with the change of impact parameter how the trajectories are resulting, and or we can say that in what
red is which trajectory?
Resulting.
Red is which
Yes,
trajectory?
So red one.
Red is NBUS, means it is no breakup scattering.
No breakup scattering.
That is elastic.
Almost. It need not be, but there is no breakup. It might have transferred some energy, but there is no.
Then you have black is.
Black is the direct complete fusion in which the complete projectile is getting fused.
That's right. Okay. So that means if you go to the third figure, your black is fusion and a red is elastic scattering.
Yes, sir.
Okay.
So as the energy is high, almost for the lower impact parameters, the trajectories are resulting into direct complete fusion.
Yeah,
as the energy
correct.
is
That's what happened. Third figure I like. That's correct. And your transfer is well set.
this green one.
Yes, green one. Okay, that's very
for
good.
the grazing like collision, the
Yeah,
neutron.
yes. So this has come out nicely. Go up. थोड़ा ऊपर जाइए.
Okay.
ये अच्छा है. इसको थोड़ा डिटेल थोड़ा करो. थोड़ा compare with some experimental number. And probability आप जो B कैसे calculate कर रहा है? B max कुछ है ना आपका?
Sir, the B max is chosen in such a way that above that value of B, almost all trajectories are resulting into the scatterings. So,
okay.
So we have considered the B up to which we are getting scattering as well as other events. So we have also calculated if we have also calculated the fusion cross section data for this reaction. Okay. Let me share the image for that fusion cross section.
आपने जो दिखाया ना बार चार्ट दिखा रहा है उसमें आपने दिखाया कंप्लीट फ्यूजन इनकम्प्लीट फ्यूजन उसका तो एक्सपेरिमेंटल डाटा होगा ना व्हाई नॉट कंपेयर दोस्तों.
So for that, experimental data are not available, sir.
नहीं है?
No, sir. But sir, we have verified. Sir,
you do some reaction where experimental data are available. Then it will be nice, no?
Sir, what we have done is we have already calculated complete fusion cross section data for this reaction, which are agreeing well with the experimental data. So which means that the projectiles and targets ground state properties are constructed properly, and for that ground state properties we have calculated this event fractions and event probabilities.
Okay. No, what I'm telling, what you have done is correct. I agree. I'm just trying to say that the calculation you have done, it will be nice if there is some experimental data where you can compare that.
Okay, sir.
So
okay.
then only it
we'll
will
look for that.
It will be complete.
Okay, sir.
The study will be, and you can say that your model is consistently able to explain the experimental data.
Okay, sir.
Okay, all the best. It's a good work.
Thank you, Dr. Nayak. So that's it. I think we have completed this poster session. Now go back to Professor Godre.
Okay, thank you, Professor Surjit, for chairing this session and being present in other sessions as well. I'm sure you would have listened to all this talk completely if there were.
Yes, I have listened only 50%. Yes.
Yeah,
that was pretty good.
So I thank both of you, Dr. B.K. Nayak and Dr. Surjit Mukherjee, for sparing so much of time. It was almost 12 o'clock in the morning till now. It is 7:15. I think DA symposium में भी इतना लंबा नहीं चलता है.
So thank you, Godre Saab, for giving us this opportunity.
Yeah, to making as a part of it. So it was anyway. Whenever there is anything academic, it is always nice to.
So nice of you, all of you.
Thank you so much.
All students will always benefited by your guidance, I'm sure.
Yes.
Whether I'm in the department or not. Once again, I thank you. And
thank you so much.
All the best.
Thank you. All the best.
Thank you, all of you.
Thank you.
Thank you.
Thank you, Professor. So we'll leave now.
All of you. Sometimes we will have tea some other day.
Sure,
yeah.
Sure.
Tea with snacks.
Now it is time.
I also thank Dr. Dimmer and other colleagues for Dimmer has really taken up this poster session. I was not knowing how it should be done in the last minute. And he came.
I think you have done nicely actually. I was telling.
Yeah.
I was thinking I can suggest our symposium guys to do this.
Yeah.
I absolutely agree.
उसका थोड़ा fine touch करना है, थोड़ा coordination अच्छा रखना है.
I think
थोड़ा then it will and you have to ask them to write in bigger letters.
Yeah, exactly.
दिखता नहीं कुछ, आँख को strain करता है.
Yeah, that is correct. That is my suggestion.
Yeah.
I will transfer this to all the students. Not
This
only
is a good. I appreciate this initiative. So that's nice. Whenever there is a difficulty, we get new ideas.
So congratulate you, Godre Saab and your team for this.
Good job done.
Thank you.
Okay.
Thank you.
Okay.
Thank you, all of you. And
Thank
all the
you.
best.
Bye.
Bye.
Bye. Bye.
Okay.
So now the session is over. First day.
Will join tomorrow at 10:30.
All the participants are requested to join tomorrow at 10:30 and 10:30, the second day of the conference. Okay, thank you all of you.
Okay, thank